this time we'll see a little bit about derivations on field extensions. So let me tell you what a derivation is. So let's assume L over K is a field extension and a K-linear map, which we call D, like derivation, from L to L, is called derivation of L over K if it satisfies the product rule, namely d of A times B is equal to A times d of B plus B times d of A for all A and B in the extension field L. Okay, now let's see some properties of derivations. So let's state a lemma. So the first statement is that the derivation is 0 for all elements in K. And the second statement is that if we have a polynomial with coefficients in K and we have an element in the field L, then the derivation of f evaluated at A is equal to f prime, the formal derivative of the polynomial f evaluated at A, times d of A. So maybe let me first give you a short reminder of the formal derivative. So this is just, let's say, maybe not f, maybe let's write it out. So if we have from 0 to n and then akx to the k, and the derivative is just the sum from k equal 0 to n minus 1 ak times k x to the k minus 1. And of course this k can be 0 depending on the characteristic of the field. Okay, so let's prove this lemma. So for the first part, this is quite easy, so let's at first show that the derivation of 1 is 0. So this is the derivation of 1 times 1, which is 1 times d of 1 plus 1 times d of 1, which is 2 times d of 1. And so if we subtract d of 1, we get that d of 1 is equal to 0. And now we look at the elements in K, and d of A is just A times d of 1, because the map is linear, K-linear by assumption. So this is 0. Okay, that's it for part A. And now let's prove part B. So first, let me tell you that it's enough to prove this for monomials, because if we have it for monomials, then here this d is linear, and also f prime is linear, and we just multiply by d of A, so the right hand side is also linear. So it's of course for let's say k linear but the coefficients are in k, so that's good. And we just show it for monomials. And well, if we have the constant polynomial 1, then we've already shown that d of 1 is 0, and here the derivative is also 0. And also for f equal to x, it's also clear. So that's good, because for f, then we have just d of a, and here we have 1 times d of a. Okay, and now we use induction. Namely, we want to show by induction that d of a to the k is equal to, let me write it in another way, k times a to the k minus 1 d of a. And if we have this, we can we see that, so this corresponds to, or maybe let me use colors. So this corresponds to this, and this corresponds to this. Okay, so that's what we want to show by induction. So for 1 and x, we already said that it's clear. So let's look at d of a to the k, which is d of a times a to the k minus 1, which is, by the product rule, a times d of a to the k minus 1 plus a to the k minus 1 d of a. So that's already fine. We don't have to worry about the second term right now. We just apply the inductive hypothesis to the first term. So we get a times, now, k minus 1, a to the k minus 2 d of a. So by the inductive hypothesis, plus a to the k minus 1 d of a, and that's exactly what we want to have. That's k times a to the k minus 1 d of a. So we're done, and we've proven this second equality. So this part B. So yeah, actually, I don't know, when I first saw this, I found this a little bit surprising, because here we have a polynomial, and here we have the formal derivative, and then here we have just some arbitrary derivation. And if you have maybe a more intuitive idea why this is true, I would be very eager to hear it. So please tell me if you have some intuition why this is true. I mean, the proof is clear, it's not that hard, but maybe there's a more intuitive way to prove this. So yeah, that's it for today. Maybe next time I'll show a little bit more about derivations, but I'm not sure about this yet. Maybe next time we'll see something different. We'll see. So thanks for your attention, and have a good time. Bye.